Hello, welcome back. All right, happy Monday. Um, we are in April already, and the semester ends in the end of April. So we have four more, well, including this week, we are having one, two, three, four weeks in total. Um, and Wednesday is our Wellness Day. So there's no class on Wednesday, and we are going to resume next week. So today we are going to finish. I hope we will be able to finish our streaming lecture, and this will be your last assignment. All right. So I hope you still remember what we have been talking about. So all the algorithms that we covered in the streaming lecture, remember? Streaming data is difficult to process because we do not know about the future, and we do not have the memory space to store lots of data so that we can look back for a long time. We only can look at a small amount of data and make decision. So that's why all these algorithms can help us to generate an approximate answer for some questions. But most importantly, we want to be able to know the error rate. For example, false positive rate, false negative rate. So we talk about Bloom filter. Here's the Bloom filter. So remember, quick recap on your Bloom filter. For the Bloom filter, you start by constructing a bit array. In the bit array, you set everything to 0. You have some hash functions. In this example, we have two hash functions. One is looking at the odd bit. The other one is looking at the even bit. So I just saw someone asking this question on Piazza. Couldn't really figure out how to generate 5 and 2. Well, very simple, right? You just take for H1, H1 you take odd position bits, H2 you take even position bits. So H1, 1, 0, 1, and you put this one becomes 0, this one becomes 0, and use this number. So even if you don't know how to generate 5 and 2, this is not very important. This is not important at all. So you don't have to care about how you generate 5 and 2, okay? You only need to know that you have two hash functions. Each of them will give you a number based on the input, and these two should be independent, okay? So in the Bloom filter, you take all the elements in your database. This is your database. Remember, the goal of a Bloom filter is for a new item comes in, new item, we want to know if the new item exists in the database already, right? And the property of the Bloom filter is somewhere here. If the Bloom filter says no, then your new item is definitely not in S. If Bloom filter says yes, it is possible that your new item is not in S. Okay, so how does this work? Your hash function is going to give you some numbers, and these numbers will be positions in the bit array. So you would just set that position to 1, right? Pretty straightforward. 5, you set 5 to 1, 2, you set 2 to 1, and so on. This filter becomes your, well, approximate records of what are the items in your database. So when a new item comes, let's say 118, you use your two hash functions, generate two numbers, look at the filter. If a position says 0, then you say, all right, this number is not in your database. However, even when you have 38, both positions are 1, it is still possible that 38 is not in your database, right? This is our false positives. So we talk about false positives. We talk about the upper bound for your false positive. So false positive rate, you have an upper bound. Most importantly, we want to be able to have a closer upper bound. So how do we do that? We did this here, right? So we consider throwing darts on T targets, right? Each dart is a hash result. A target is a bit position in your bit array. So based on all this calculation, we have an upper bound. Based on the upper bound, we will be able to start to estimate the fractions of ones and the error rate. All right, so what is the error rate? Instead of having this in our original estimation, now we have this, right, based on the dart and target. So your false positive rate is this. And this is when multiple hash functions hit the same bit. So just be extra careful here. This is your upper bound. This by no means is your true false positive rate. But upper bound is useful because when you have the size of the bit array, the number of hash functions, the number of elements you want to insert, you can estimate your error rate, your false positive rate, and to decide if you want to use a longer hash function. Well, usually this depends on your memory, or you want to use more hash functions. This depends on the computational complexity, right? The time of the computation you want to do. All right, so let's look at one example. Say if your n is 8 billions, you have 8 billion bits in an array. Your items is 1 billion. You have 1 billion objects in your set, and you have only one hash function. So recall this is your false positive rate, right? Based on the function, the probability function we just derived. And you can look at what if k equal to 2. Right now you have 0.1175. When k equal to 2, you have 0.2212 squared equal to 0.04, right? Smaller. You can keep going and you will be able to say, all right, the optimal k when the n is fixed and m is fixed, the optimal k will be this number. How do we know? Well, here. This is your target function, your error rate, and based on your m, based on your n, you can rewrite it like this, right? Put your m and n. You have here a function. You have one variable. How do you find the minimum or maximum? Well, you take the first derivative, like what we did before. You find where you have a slope of 0 and figure out if it's the minimum or maximum. In this case, this is the minimum. So this is when your k is 5.54, you are going to have the smallest error rate, right? All right, so what have we learned here? We learned that Bloom filter is pretty cool. You spend some time to construct your bit array and do all these hashes with all the items you have in your database. When a new item comes in, you basically only have to do k operations, k lookups, because each hash function will give you a position in the bit array, and you do a lookup to see if you have a 0. So at most, you do k lookups, and you will know if that item is in your database. You do have some false positives, and you will need to be able to minimize your false positives, given that you already know how many bit arrays, how many bits that you can use in your bit array, and how many items you have in your database, right? In this case, you can rewrite your error function like this, find the minimum, and that will be your k, okay? All right, cool. That's your Bloom filter, very easy. So the next topic I want to talk about is counting. We want to be able to count your element in your data stream. So what does counting mean? So the first type of counting is to count the number of distinct elements that we have seen so far. It could be the number of distinct users to Facebook in the previous 10 hours. Number of distinct queries submitted to Google in the last 2 days, right? So distinct is important. Obvious solution is when a new item comes in, we will just hash this new item into a table of distinct element. And if the table says, I don't have this element, you will just insert new record in that table, right? So this way your hash table basically keep all the distinct element that you have seen so far. If a new element is not in the table, you just count it. If it's already in the table, you do not count it, right? So this way you have a table to store all the elements you've seen so far, and you also have a counter to say how many unique items you have seen so far. So, but what would be the problem of this approach? All right, Ting Wei is good. We cannot save all elements in the hash table, right? Think about in the past 2 days, maybe you have 2 billion elements inserted, and 2 billion is a lot, right? If you need to use 8 bytes, that will be 8 million bytes. You cannot really put them all in the main memory. You probably need to store them in the hard drive. And next time when you want to check, you have to read data from the hard drive into the memory, compare, save it back to the hard drive. So not a good solution. So how do we deal with this problem? What would be the algorithm that will be able to give us an approximate number of distinct elements and also tell us the error rate? Here's the algorithm, very simple. The algorithm helps us to estimate the count of unique elements that we have seen so far. It has 3 steps. The first step is when an element comes, you hash it into a sufficiently long bit string. For example, you just generate some hash function, and this hash function will take an element, could be a string, let's say a username or user ID, because you want to find the number of unique users in the past 2 hours. Okay, so you take the user ID, and the hash function will convert the user ID to a bit string, let's say 4-bit. And you add a counter. This counter is R. This R is the length of the longest trailing zeros in the bit. In this case, if this is your bit string, R would be 2. So far, so good. And when the next stream comes, if you have 1, 1, 1, 0, your algorithm will look at this string, bit string, and says, all right, longest trailing zero is 1, so I'm not going to update this number. I throw this away. The next one comes, it's 1, 0, 0, 0 compared to here. I have 3 zeros, you have 2, so I'll just update you to 3, throw this away. Okay. So pretty cool. Every time you only maintain this number in your memory. Okay, so 2 questions. R equal to 2 means hash value has 2 ones. Okay, no, here. Length of the longest trailing zeros. Zeros, not ones, from the right. From the end of the string, you count how many zeros you have. So left to right instead of right to left, right. Well, right to left. You start from the end and you look at the length of the zeros. Okay. If you have 0, 0, 0, 0, R equal to 4. If you have, say, 1, 1, 1, 0, what would be your R? Well, it could be 1, but if you already have 4, it would be 4. Christina says, isn't left the end for bits? I'm not sure why the left is the end of bits, but usually the right is the end of the bits. All right, so anyway, it doesn't matter. The algorithm works like this. You read from the right to left and count how many zeros you have. All right, that's the algorithm. And when you want to estimate the count, you just do a 2 power of r, before, and that's your answer. That's it. All right, let me do this again. You want to estimate the number of unique items you have seen so far. Every element, you convert it to a string like this. You read from the right, you see how many zeros you have. In this case, you have 2, you just set it to 2. When a new stream comes, when a new element comes, you hash it again into the string. And if you have more zeros from the right, you just update this number to 3. If you don't, you just keep 2. Okay. So what's our memory consumption here? What are the things you have to store in your memory? Anybody? You don't have to store the hash value, right? All right, so still have a question. How do we count distinct by giving out this number? Still confused. Okay, I haven't explained why this works. Let's say from until here, anybody has questions? How do we generate the R? We only store R. So the answer is we only store R in your memory. So this is your memory space. Well, you also have to store a hash function, but hash function generally doesn't take much. So anybody has questions until here? Okay, great. So this is the last step, is once you see enough elements, say after 1 hour, you want to estimate how many unique elements you have in this 1 hour, you just do 2 power of R. For example, if your R is 2, then you have 4. Then you have the estimate of a unique element. Okay, that's the entire algorithm. What I haven't tell you is why this works. So let's look at some examples before we explain why this works. Say consider 4 distinct elements. You have A, B, C, D. You hash their values into bit strings of length 4. Right? Remember I said you can decide on the length of the bit string that you want to have. So our question is, how likely do we see at least one hash value with a 0 in the last bit? Okay, last bit. That'll be on the next slide, but you just look at some examples here. A, B, C, D, say hash A is 0010, hash B is 0111, hash C is 1010, and so on. Okay, so this is a made up example. Don't think too much about it, but let's look at this. Say at least one ends with 0. We want to have the probability of none of the hash values ending with 0. So how do we generate this probability? That means every string ends with 1. So ending with 0, the probability ending with 0 is 1/2. The probability of ending with 1 is 1 minus 1/2. Well, it's the same, right? So it's 1/2. And you have 4 strings, so power of 4. Cool. You have the probability of none of the hash values ending with 0 because you only look at one element. The probability of at least one ending with 0 is 1 minus this, right? The complementary probability, because this one says none, and the one that the probability we actually like to have is at least 1. So cool, you have this. So the probability of having 4 strings and at least one of them would end with 0 is 0.93. How about 0, 0? The probability of someone ending with 0, 0 is 0 times 0, right? This is 1 over 2 times 1 over 2. So it's 1 over 2 to the power of 2. The probability of none of them ending with 0 is, okay, 1 does not end with 0, power of 4, because you have 4 strings, and 0.32. So this is none ending with 0, 0, and at least one ending with a 0, 0 is to take the complementary probability of this is 0.68. Okay, pretty cool. You just need to look at how this changes when we start to look at more zeros. Another one, what would be the probability of at least one ending with now 0, 0, 0? Okay, so someone ending with 0, 0, 0 is 1 over 2 to the power of 3. None of them ending with 0, 0, 0 is this, power of 4, because you have 4 strings. Complementary probability will be 1 minus 0.59 will be 0.41. All right. You see the probability start to get smaller because now you have longer zeros. So why does it work? Why this algorithm works? Well, if we look at the probability of HA, the hash function, taking A and generate an input, having at least R trailing zeros, this will be 2 to the power of minus R, this. Right? Like in our example, if you have 3 trailing zeros, this is 3. Suppose there are m distinct elements, it becomes this. Remember what we did on the last slide? First, the probability of someone has trailing zeros of some length of R, and you have m strings, and you can take the complementary probability here. This is the probability that your hash function A for some element A has at least R trailing zeros, as in the example in the previous slides, right? In the previous slides, our m equal to 4, and we keep changing R from 1 to 2 to 3, right? So the general case, if you don't know about your number of strings, you don't know about the R you need, this is your general case. We can rewrite this because this is our good friend. The Euler number is when you have 1 plus 1 over n to the power of n. When n is really large, well, to the infinity, this is your Euler number. So let's rearrange all these terms here and make it a Euler number. It becomes this. How does it become this? We have 2r, 2 power of r, 2 power of r, right? Now you have this, you have this. Start to look very similar to this. Then you can rewrite it. Okay, so the probability that your hash function for some element will have at least R trailing zeros is this. And this probability depends on your M, the number of unique items you have, and R, the longest trailing zeros you are looking for. So given this that we just saw from the last slide, if we look at our good friend, the Taylor expansion for your e power of x, it becomes this. However, well, this is this. If your x is much smaller than 1, then this is very small, this is very small, and all these are very small, so we can ignore them. We can say e to the power of x is approximately this value, 1 plus x, okay, when your x is very small. So if you look at here, do you have e to the power of x? You do. You have e, and this is your x. Right? So you can rewrite the entire function with the Taylor expansion. Your probability becomes this, becomes 1 minus, what is this? This is your Taylor expansion. You have a 1 here, right? You have a 1 here. This is your x. This is your x. Rearrange all the terms, 1 and 1 cancel out. Minus sign, you have this. So eventually we derived that your probability equal to m over 2 to the power of r if 2 to the power of r is much larger than m. Why? Well, because this approximation only works if x is very small. And what is our x? Our x is this term. For this to be very small, your 2 to the power of r needs to be much larger than m. Okay, all right, cool. What have we learned so far? We haven't explained how the algorithm works yet. We only work on some probabilities. So we know this probability, the probability that a hash function for some element will generate at least r trailing zeros is this, okay? This probability depends on r, the length of the zeros you are looking for, and the m, the number of unique items you have seen so far. Cool. Based on this, we arrange all the terms to this. Why do we want to do this? Because we want to have a Euler number here. When we have a Euler number, we can have Taylor expansion of the e to the power of x and rewrite the entire probability to this. When 2 to the power of r is much larger than m. All right, cool. So we learned a couple of things. But why does it work? Again, the probability that the hash function for some element a will have at least r trailing zeros is this. So the complementary probability to this is the probability that the hash function for no element a will have this r trailing zeros, no element, right? So it'd be 1 minus p will be this, right? So this cancel out, and you have this. Cool. All right, we have this too so far. And this is to show you why it works. So based on this probability functions, we know that if 2 to the power of r is much larger than m, then p will equal to m over 2 power of r, right? This is our p. It will be this based on the Taylor's expansion. And because 2 to the power of r is much larger than m, this will become 0. And your p prime will be 1. What does it mean? Well, this means if 2 to the power of r is much larger than m, then we will not be able to see this trailing zeros of r trailing zeros, because it's too long. So the probability of finding a tail length at least r approaches 0. This tells us that your r is unlikely to be too large, right? If r is too large, this will happen, and the probability will become 0. You will never be able to find it. So r is unlikely to be too large. So 2r is not going to be much larger than 2 to the power of r is not going to be much larger than m. Cool. How about if 2 to the power of r is much smaller than m? Well, in this case, this is your p, And if this is much smaller than m, this term becomes 0, right? You have 2 to the power of r, you have m here, and your p will becomes 1, and hence your p prime, your complementary probability becomes 0. What does it mean? Well, this means the probability if 2 to the power of r is much smaller than m, the probability that we should find a tail of length at least r approaches 1. Okay, this means if your r is very small, it's very likely, almost 100% guarantee that we are going to find it. So since r by definition is the longest zeros, we are not going to look for short ones. It is unlikely to be too small. So this will not happen. And based on these two cases, we know that your r is unlikely to be either too high or too low. So we say your 2 to the power of r is around m. That's why you can use 2 to the power of r to estimate m. Okay, so that's the explanation why you can use the 2 to the power of r to estimate m. What would be the problem in combining all this estimate? Well, usually you would just take like our min hash examples, you hash multiple times. You would take this average of 2r values, right? So instead of storing an r in the memory, you can have r1, r2, r3, and every time you have 3 hash functions, h1, h2, and h3, and all these r's are giving you the longest tail zeros, the length of the tail zeros you would have based on each hash function, okay? And because these are different functions, hash functions independent, so you can have 3 very different values, then how do you estimate with 3 values? Can you just take an average of them? Well, the problem of taking an average is the expected value of 2 to the power of r is actually infinity. Because when your 2 to the power of r is larger or equal to m, when you increase your r by 1, the probability of finding that zeros, that tail zeros at the length, it's smaller, but this estimated m will be double, right? Let's say your original, your r equal to 2, your estimated element is 4. When you increase your r by 1, say 3, now you have 8 element, right? So every time you increase only 1 in your r, your estimated element becomes double. Although your probability does not change that much, right? Only changes here. So the contribution from each large r to this estimate will grow when your r grows, and you can have really large 2 to the power of r's, right? Because we know this estimate is not very accurate. It's only an estimate. If you run it many, many times, you're going to have an outlier, and that outlier could be very large. If you take an average, one outlier can screw up your result. So how do we do this? Well, sometimes people just take a median. For example, let's say this is your 2 to the power of r values. You can have 2, you can have 4, you can have 8, 16, and so on. Okay, you have some value here. But somehow some hash function give you a really large number, 10, 24. If you're going to take an average of all these values, your average is probably somewhere here, right? Although we know this is outlier, most of your data point is here, we still cannot use average to correct this estimate. So how do we do this? Sometimes people take median. Median means you just count how many points or how many estimates you have. You take half values, and usually it works. But what would be the problem of taking median? If we take average, you will have when you have one very large values, your estimated result will not be good because the outlier will skew your result. If you take median, all your values are actually just power of 2, right? You just estimate with 2 to the power of r, and you can see there's a huge gap here. You cannot estimate anything between here. So the solution is actually very easy. You take all the result here, you do a clustering. You can do a k-means clustering or hierarchical clustering. You group all this result into small groups. You take average for each group, then you take median of the averages, right? So for example, in our example, you have 1024 here, and you have a bunch of small ones here. If we do clustering, we identify one group here, we identify one group here, we take the average value here, we take an average value here, and we find the median. Not a very good example because only 2 values. Median, we can probably pick the first one. If you pick the first one, you're lucky. If you pick the second one, this is your outlier. But usually you will have more than 2 groups, so you should be okay. All right, so that's the algorithm for estimating the number of distinct values. And the next algorithm that I am going to talk about is to estimate the moments. This one is actually very fun and also very simple. So what is a moment? The moments are very useful estimates for data stream. Also, not just for data stream, when you have a series of numbers, time series as well. Even if you look at your data offline, you can use moments to help you generate some useful statistics of your data. So what are moments? Say you have a stream S of elements drawn from a universal set, V1 to Vn. That means your data stream can only contain elements V1, V2 to Vn. Mi, we define Mi is the number of occurrence of Vi in S. For example, if this is your data stream, you have 1, 4, 1, 3, 4, 1. What would be your universal set? Well, in this case, your universal set would be 1, 3, and 4. Okay, because that's the only element you can have in this case, because that's all the things that we see so far in your data stream. What would be the M's? So what would be your M1? Well, in this case, 1, your element 1, your V1 is 1, right? The number of occurrence of 1 in the data stream is 1, 2, 3. So M1 is 3. What is M2? Well, what is V2? Well, if you look at your data stream, V2 is 4. What is the occurrence of 4? That will be your M2, 1, and 2. That would be 2. Cool. That's your M. So now we know what M is. We can define your moment. So for moments, we have kth moments of S. So kth moments of a data stream, and that K can be from 1 to a higher number. And it looks like this. You just look at all the element types you can have in the universal set. You add up all the values. The K is your power term here. But what does this mean? Why is this important? If you look at the 0 moment of your stream, okay, here, when K equal to 0, Mi becomes what? Anybody? Great. So Shenmin says when K equal to 0, Mi equal to 1. And what is this? Summation of ones. This will be N. This will be the number of distinct elements in S, right? What would be when you have first moment when K equal to 1? That means you are adding up all the elements there and there, all the occurrence, well, the occurrence of every element together, that will be the length of your data stream, okay? So cool. This is nice length is nice, but we can calculate it in some other way and doesn't sound very exciting. A really cool moment that you can use and people use it very frequently is the second moment. This is the sum of squared frequencies. Remember, when we look at squared values, it always tells us something. When you do RMSE, when you do sum of the squares in our clustering example, right? The second moment of S is the sum of squared frequencies, and this is also called the surprise number. The surprise number measures the evenness of distribution of some elements in your S. What does it mean? Look at here. Surprise number. Let's say you have a stream of 100 elements and you have 11 values appear in this 100 elements. Unsurprising, you have 11 values here. These are all their m's, the frequency when they appear. So you don't care about the order now. This is only the number of frequency, right? The first element, the first values appear 10 times. Second to the last values appear 9 times, right? Pretty even. None of them are more frequent. So the surprise number is 10 to the power of 2 plus 10 times 9 to the power of 2, right? This is here, this is this, and you have 10 nines. Now the surprise number is 910, okay? Remember, this is your moment, and when k equal to 2, this is your surprise number. So what would be surprising when you have something like this? The first value appears 90 times. All other values only appear 1 times, right? This is very uneven. The first one is so frequent. And the surprise number will be 90 to the power of 2 plus 10 times 1 to the power of 2. This is 8110, right? Much larger than this. And this is mainly because you are doing all these squares. And if you have a large number, the square is even larger. So you have a surprise number that is surprising. So cool. Now we know this surprise number is important, but how do we measure it? The AMS algorithm tells us that we can estimate the second moment of a stream of length n, and it can actually be extended to estimate other types, other element, the other moment. And the algorithm works like as follows. You pick k random numbers between 1 to n, right? Because you know the stream length is n. You pick k numbers. You construct a variable x at some time t. You record the count from position t as x value, right? That means now you establish a counter. When you start to see more values in the stream, you just increment the counter. At the end, when you don't have the stream anymore, after n, when you want to estimate the moment, you just use this function. You take every x value, you take 2 times every x value minus 1 times n, sum them all up, divided by k. This is your second moment, okay? And we're going to explain how this works in the next slide. But before that, let's take a break for 10 minutes, come back at 7 p.m. If you have any questions, feel free to put it in the chat. Yes, yes. All right, I'm back. All right, let's come back to our algorithm. Again, this is also our usual style for the streaming algorithm. This is the entire algorithm, but this might not be very clear. This is to help you understand. Well, let's look at the example. All right, here. So say this is your data stream and you want to estimate the second moment of the data stream without really counting all the m's and do a sum of squared. So let's say your stream length is 15 and A occurs 5 times, B occurs 4 times, C and D each occurs 3 times. Your second moment is this, right? So how do we know? Well, remember your M. Now you want to count MA, MB, MC, and MD. So how do you do that if you have enough memory space? starting from here, you see A, you create a variable MA, you set it to 1. Now you see B, you set it to 1. C, set it to 1. You look at B again, so this becomes 2. You have D equal to 1. A, this becomes 2, and so on, right? So eventually you're going to have this. Then you can calculate your second moment, okay? But the problem of streaming, the stream data is the same. You don't have enough memory space to store this, so you want to estimate your second moment. So how do you do that? You start by setting some random variables. Well, these are some variables in your memory that you can record something. In this case, we are going to record two things for one random variable. You are going to record the element, right? The element that you see at the time when you introduce this variable. Also the value, this will be the number of occurrence of your element X from time t to time n, right? So this is usual, you just count them. Your X value will be 1 at time t when you first introduce that variable, and you will increment the variable when you see another element of the same. Let's look at one example. This is your stream. Suppose you keep 3 variables, right? So instead of keeping one variable for each distinct element, now you only have 3 variables, x1, x2, and x3. You introduce them at different positions. So first one here, second one here, third one here. Cool. All right, position 3, you introduce x1, so x1's element equal to c, right? You have a c here. And the value is 1 because this is the first time you introduced the element. At position 7, so 3, 4, 5, 6, 7, you see another c. You're going to increment your x1 value to 2, right? Fairly simple. At position 8, you introduce the second element. This element is d because you have d here. The value is what? This is the first time you introduce the element. At position 11, so 9, 10, 11, you have d, you increment the value, 12. You see c again, you increment x1's value because x1 is c, right? x1 dot element is c. Now position 13, you introduce another element. This time you have a. x3's value is 1. At 14, you see an a again. You increment the value to 2. That's it. So if you look at this example, you only use 3 random variables. And every time when you introduce a random variable, you start to count how many times this element occurs till the end of the string, right? So position 3, you are going to count c. So 1, 2, 3. x1 will be 3. x2, position 8, you're going to have d. So 1, 2, x2 will be, x2's value will be 2. x3 will be introduced here, so you're going to record a, 1, 2, x3 will be 2. And you do not count, in this case, you do not count b, you do not count d, because when you introduce the random variables, they are not at the position. All right, so once you have all these 3 values here, now you want to estimate the second moment. You take the equation. I haven't told you why we have this equation yet, but let's just look at the example. You take the equation, you say, all right, you have the value, so 2 times this value minus 1, and n is the number of elements that you have seen so far, so 15. For x1, your value is 3, right? 2 times 3 is 6. 6 minus 1 times 15, you have 75. X2 and X3, your value is 2. 2 times 2 equal to 4 minus 1, you have 3 times 15, you have 45. So you have 75, 45, 45. You sum them up, divided by 3, you have 55. This is your estimate. This is the expected number. Why do we call it the expected number? Well, because you have 3 values, you just sum them up, divided by 3. It's the same as you say, all right, 1 over 3 times 75 plus 1 over 3 plus times 45 plus 1 over 3 times 45, right? You have 55. Cool. So your actual value, if you record everything, it's 59. So we are very close. But why does this, we know how does this work, but why does it work? Let's look at the algorithm again. This is your data stream, and you introduce three random variables, and let's look at some terminologies. So first, you have EI. This is the element that appears in position I. And this is a random variable introduced at the position. It will have something like this, right? So for example, E3 will be C. And CI is the number of times that EI, or in this case, C, appears in position from I till the end. That will be your X value. If you look at C3 this is C3 will be what? 1, 2, 3, right? C3 equal to 3. So what will be E6? E6 is 3, 4, 5, 6. E6 will be A, right? The element is A. And C6 is 4. Why do we have 4? 1, 2, 3, 4. Cool. All right. So this is just some terminology that we are going to use on the next slide. So your element and your occurrence. So if you start from the beginning, let's say if you have enough random variables, you have unlimited memory space, you can create unlimited random variables. Let's create a random variable at every position. So your E1 will be A, right? The element at position 1 is A. What will be your C1? The number of occurrence of the element at location 1 will be A, 1, 2, 3, 4, 5. And this is actually your MA, right? This is the number of occurrence that A appear in the data stream because your counter introduced at the first time when you see A. All right, cool. What about E2? Element 2 here is B. What about your C2? Is 1, 2, 3, 4. It's 4. And this is your MB. Why is this your MB? Well, because this is the first time you see B in the data stream. E3 is C. C3 is 1, 2, 3 equal to 3, and this is your MC. E4 is B. All right, you already seen B again. So this counter is definitely not your MB, right? This is your second time. This is the first time. This is second time. So this is MB minus 1, right? Let's verify it. So B, 1, 2, 3. So this is 3. This one's 3. What is your MB? MB is actually 4. And this makes sense, right? Because at position 4, this is your second time when you see B. So the counter, the occurrence will be MB and minus the previous times that you didn't see B. And you can start to look at this, you will start to have MA, MB, MC, MB minus 1. What will be the next time? Well, next time you have D, so you're going to have MD. And the next time you have A. And since you already have A here, so the counter will be MA minus 1. Pretty cool, right? If you look at all this, eventually the last element, the last time when you see something like here, your E14 will be A, and your counter will be what? Will be 1, because this is the last time you see A. E15 will be B, and the counter will be 1, because this is the last time you see B. So if you sum up all these numbers here, what would you have? Oh, sorry. What would you have? You're going to have MA, MB, MC, MD, MA minus 1, MB minus 1, MC minus 1, MD minus 1, MA minus 2, MB minus 2, MC minus 2, MD minus 2, until what? Until the last time you see this variable and you have 1. All right, so this is a property when you have unlimited number of variables. So what would be the estimate? When we look at our estimate, this is the function we use to estimate it, the second moment. If we look at this, this is here. And here is take the summation and divide it by k when you have k variables. So it's the same as you take the expected number of this. Okay, and this is the average over all positions I between 1 and n, right? Because you're taking averages. And if you look at this part, it becomes this. So why do we say average over all positions? This is the average. This is the summation of all positions. And this is your counter, right? So don't get confused here. This one is directly from our equation. So we haven't talked about why you have 2c minus 1 yet. Okay. All right. So if you look at this, you can take the n out, divide it, cancel these two terms, and it becomes this. All right. So what is this? Remember in our last, from our last slides, we know that your CI, if you have enough variables, it becomes from 1, from 2m, sorry, from 2m to 2m minus 1. Oh, no, from m, let's say MA to MA minus 1, MA minus 2, MA minus 3 till 1, right? So this is your MA. MA minus 1 didn't show up here, MA minus 2, and you have 2, then you have 1. How do we know this is 2? Because when your CI has 2, 2 times 2 minus 1, you have a 3. When you have CI equal to 1, 2 times 1 minus 1, you have a 1. Okay, so this is for every x, for every distinct element you have. This is actually this. The summation of from I equal to 1 to mi, the summation of 2i minus 1 can be rewritten to this, and it's mi squared. So this is actually the summation of mx squared, which is your surprise number. We are going to look at this again next week, when we have more time, there are more examples on the slides. Yeah, that's it for today. And we are going to have our quiz. Any questions? All right, so before you can go on your Blackboard to find the quiz. And before you do your quiz, I want to say that please make sure you work on your homework assignments, read your textbook, make sure you understand your quizzes. If you don't understand your quizzes, you can ask on the Piazza, and also you should go to your office hours for your graders. If you see, wait, let me see if you have quiz. Okay, you should have your quiz. You should see your quiz 10 on Blackboard. So make sure you understand the material. You should be able to see your quiz now. Make sure you understand the material and read the textbook. I don't want you to spend too much time for the preparing your comprehensive exam. If you already know this, you shouldn't have to spend too much time for your comprehensive exam. All right. I hope you all learned something today, and I'll see you next week. Oh, you have until 8 p.m. for your quiz. Your TA is here, but let me quickly go through your quiz. You should be able to see the screen I'm sharing, which is your quiz. All right, the first question asks you to compare BFR and the keyword algorithm. Your description should include a discussion of their data assumption, right? Because that's the most different part. The part that's make them very different is the assumption of the input data, and also how they represent a cluster in the memory, how they summarize a cluster in the main memory. Then the second question is Bloom filter. We talk about this today, but I want you to be able to show this fraction of ones. This is a probability that the bit in array is set to 1 by at least one hashing. So how do you derive this? Right? Remember the Dart and target example. The third question, I want you to explain the reservoir sampling in stream dataset. Prove this property by induction, right? By induction, you start by having n equal to the sample size, then you do n plus 1. The last question, we discussed the following example for your stream sampling, right? The first part of the stream class, we look at some scenarios. In this scenario, we want to find duplicate functions. We say we have space to store these query streams, but it didn't work. So why didn't it work? I want you to show that this sampling by position is problematic, and I want you to be able to describe a solution. You can use an example. You don't have to. Every time when I say you can, that means you don't have to. But if you use it, it will be easier to explain. All right. Thank you, everybody.
It's 8 o'clock, so please upload your solutions to Blackboard. Thank you.